So next report is Kaveh Eftekharinasab. Kaveh, please.
Thank you. The talk is about some abstract critical point theorems which are obtained by using the topological notion of linking sets for infinite-dimensional Frechet manifolds. The theory of linking sets is a systematic way to locate critical points. It was introduced in the late 70s by Benchi and Rabinovich. The idea behind this theory is pretty straightforward. Well, I will explain roughly the idea, then provide with the precise definitions. Well, the idea is if A and B are two subsets of space X, then we say A links B if for each differentiable functional phi over X that satisfies the equation, the inequality 1, there is a sequence X sub n in X such that phi of xn approaches to a constant and phi prime of xn approaches to 0. Now, if such a sequence, if every such a sequence has a convergent subsequence, then we obtain a critical point. And in this case, we say that the functionals satisfy the compactness condition of Pallas and Smale. This condition was introduced in mid-70s by Pallas and Smale when they tried to extend the Morse theory to the infinite-dimensional manifold. So, in order to apply this theory, first we need to find linking sets, which is not an easy matter, and it depends on the geometry of the space and the structure of the functional. And then once we have a linking set, then we need to verify the Pallas-Smale condition, which is also not easy matter. So far, it has been introduced different notions of linking sets. Homotopical, cohomological, isotopic, and so on. But essentially, the idea behind it is that, behind all of them, is that a set A links set B. If A cannot be continuously shrunk to a point without intersecting B. And this implies that A links B in the sense that I said earlier, in this sense. So it will provide us such a sequence. Now, if we can verify that this sequence, if we can verify that the functional satisfies the Pallas-Smale condition, then we get the critical point. Well, that's the whole idea of this theory. Well, so far this theory has been very well developed for the case of Hilbert and Banach spaces and manifold, and we want to try to extend it to the more general case of the Frechet manifold. Okay, well, there are various notions of differentiability for Frechet spaces, but the one that would provide a solid framework to study critical points would be the so-called Kähler C sub S differentiability. What a reason for this is that in this definition, the derivative is supposed to be belong to the space of the continuous linear mapping topologized by the compact convergence topology. And indeed, to define the Pallas-Smale condition, we need a topology. And a compact convergence topology is a very good topology to work with. And furthermore, this notion of this notion of differentiability is equivalent to the differentiability in the sense of Michael and Bastiani, which many people work with in Frechet spaces who use this definition, because for this definition, there's deep theorems of inverse theorem of Nash and Moser are available. But at that definition, we don't use the topology on the space of continuous linear mapping. Which is essential for us here to develop the critical points theory. So we will use this type of differentiability. A significant notion that we need to develop the critical point theory is a Finsel structure. A Finsel structure is a collection of functions on tangent bundle that, roughly speaking, the restriction of this function to each tangent space provides a collection of semi-nodes that generate the topology of the modular space. And this collection of functions locally, they need to satisfy this squeezing condition, well, condition 2. And on regular and paracompact manifold, there exist Finsel structures. Once we have a Finsel structure, we can define the length of a curve with respect to each component, and we can define a metric here in equation 3, a metric that generates the same topology as the original topology of the manifold metric in the equation 3. And this metric is called the Finsel metric. And I should emphasize that the theory of the Finsel geometry, there is a significant differences between this Finsel geometry in finite dimension and finite dimensional geometry. Okay, so our framework to work with will be the Finsel manifold, the complete Finsel manifold, and we use the notion of the Kähler differentiability, C sub S differentiability. Okay, well, there are substantial differences between the theory of critical points for Hilbert and Banach manifolds and the Frechet manifolds. A huge part of the critical points relies on the deformation technique along with the gradient or pseudo-gradient flow. But this is not the case for Frechet manifold, because the concept of pseudo-gradient flow requires the Finsel structure on cotangent bundle. But for cotangent bundle, we can define, for Frechet manifold, we can define cotangent bundle as a set-theoric bundle, but it does not admit the smooth manifold structure. So the concept of pseudo-gradient pseudo-gradient flow makes no sense. And also, it puts in question how to define the Palacis-Mate condition, because the Palacis-Mate condition needs a Finsel structure on cotangent bundle, which we, because of the deficiency topology, we cannot define cotangent bundle, and consequently Finsel structure on cotangent bundle and the concepts such as the gradient flow, pseudo-gradient flow, and the Palacis-Mate condition. Well, there are big differences between Frechet case and the Banach and Hilbert space. Now, the idea to define the compactness condition of Wallace-Smith type is to associate to each functional an auxiliary function in equation 4. Function in equation 4. And by using this an auxiliary function, we naturally can define the Wallace-Smith condition. And one main feature of this auxiliary function is that on sets when the functional satisfies the Wallace-Smith condition and has no critical point, this auxiliary function is negative. And this is a key point to prove the minimax principle. The minimax principle is the statement of the theorem. The minimax principle, it characterizes a critical value of a functional as an expression in equation 5. This expression, or a suitable class of subsets of the manifold. This principle, this expression now widely known as a minimax principle. This principle first was proved for the case of the Banach manifold by Lustering and Schreinerman, and it plays a significant role. This principle is a significant role in the critical points theory. In our case here, we generalize it to the Frechet manifold, but here we have a bit restrictive assumption that we suppose that our functionals must be closed. Which is in practice maybe difficult to check that the functional is closed, and is a bit restrictive assumption. However, unfortunately, it cannot be weakened. This assumption. This is an essential assumption to prove this theorem. Okay. As I mentioned, there are different notions of linking sets, but the one which would be convenient to work with this principle, minimax principle, is the homotopical one. This is the formal definition of the linking set, homotopical. It was given first by Benchi and Rabinovich, but not in this form. It is a bit restrictive form, but over a year it has been developed, and now the more realistic definition is this one. That if we have a set S sub 1, S, which is the subset of S and C of the Hausdorff topological space, we say that this pair links homotopically to the set C through a continuous function from S sub 0 to T if these two conditions hold. Roughly speaking, it means that the set S and set S and C cannot be slipped away by the function gamma. They cannot pull apart. And this set these linking sets, they will provide us a sequence that, well, as in the first slide, the sequence that f of x sub n will approaches to a constant and a frame of xn sub approaches to 0. So then we will need to verify the polynomial condition. Okay, now.
Sorry, what is H calligraphic here in the condition L2?
Here.
Okay.
Yes, this is a space of continuous function. So that the restriction of H to the boundary of S sub 0 is gone. No,
okay, so
and well, and a simple example here. If we have a set A consists of 2 points, E and F, this set homotopically links to the set, the boundary of set B here, whereas B is the neighborhood of point E, and F does not belong to the closure of B. Well, this is a simple example of the linking set, and this happened in the mountain pass lemma. This is the situation of mountain pass lemma. Actually, the idea to define the linking set was the patterns which were observed in the mountain pass lemma and the saddle points theorem. That patterns led to this idea of defining these sets. As we will see, the mountain pass lemma is quickly will be well. I will now explain the main theorem. Well, the main theorem is that if we have a Frechet manifold with complete Finson metric, and we have a functional closed, and suppose we have a linking set through some function, and there are sort of these conditions are held. Again, this theorem guarantees a critical value which is determined by this minimax expression, in equation 6. So no different linking sets will provide us with different results. As one of them that which quickly we can obtain from this theorem is the mountain pass theorem. The mountain pass theorem. To obtain the most theorem, we choose this linking set that S is the so I will, as I'm short in the time, if we can choose this simple this linking set, then the mountain pass theorem follows easily from this principle. Well, this principle, the linking theorem, is available for Banach manifold. There are different versions of this theorem for Banach manifold and Hilbert manifold. I know we proved it for the Frechet manifold. And also, the mountain pass theorem has several interesting consequences. One of them is to prove three critical point theorem that says that a function that satisfies the polynomial condition, it has two minimum, then it has one more critical point. Which is proved by the mountain pass theorem. Another interesting fact that can be proved by using this method is the answer to the very classical problem in topology, that the condition, the sufficient condition when a local diffeomorphism is a global one. Here we provide a sufficient condition that we associate to each local diffeomorphism a certain well, it's functional. Well, the functional phi here, and if this functional satisfies the Policy-Smith condition at all, well, then the local diffeomorphism is a global one. Well, actually, this is the starting point for me to study this theory. Well, some years ago, I proved this theorem for the case of Frechet spaces by using the mountain pass theorem. Well, again, in this mountain for Frechet spaces, but the mountain pass theorem, the proof was very technical and it is very lengthy. At that time, I didn't know about the linkings, this theory of linkings, so that it can be easily be proved by this technique. Now that I was discovered this theory, and and it showed that this theory also, well, of course, under some restriction assumptions, play well for the case of Frechet manifolds. Okay, I think I'm short in time. Well, that's all. Thank you.
Thank you. Thank you. Questions? Report? Please, Andrei.
Maybe it's a very naive question.
Yes.
I'm curious about this statement that if we have two different minima, then there is another critical point.
About critical point.
Exactly, the critical point theorem. If he has two minima, then phi has one more critical point. My intuition from Morse theory would tell me that one can say more, that this critical point is maybe neither minimum nor maximum. So my question, can one say, for instance, that there is one more critical point which is not a minimum?
Well, I suppose yes, but I have not the proof for it. That is my next plan for research, to study the structure of, well, you see that this linking, they don't provide us the type of the critical points. So that's for my future plan to study what is the type of the critical will be. Either it will be the minimum, it will be saddle point, and so on. Well, that's for my future plan. For now, I cannot answer to that. Well, but actually, it is very good question. That was it was studied by Hofer for Banach spaces, Banach manifold. It was studied by Hofer. He studied the structure of the critical set was obtained by this minimax expression. Well, but for the Frechet case, well, it is my future plan to study it. Yeah.
Okay, thank you very much. Very interesting. Thank you.
Thank you.
Maybe Andrei, and maybe from the proof of this theorem is based on that mountain pass theorem, and
yes.
from that theorem one maybe could see that actually it is not a local minimum. It looks like a saddle, because near it is a limit of paths which are of this kind and of this kind.
Yeah. Thank you.
But well, it is not always the case, I assume. Well, I think that as I remember the paper of Hofer, he proved that there always exists a saddle point, but I'm not sure about that. I need more investigation.
Okay, thank you. Thank you very much.
Thank you.